This is our last video for waves. Today, we're going to be dealing with harmonics. So harmonics are different standing waves that are created by having different wavelengths and different frequencies. So we're going to see how we go from the first harmonic to the second harmonic to the third harmonic and so forth down the line. Alright, so we're going to start off with harmonic waves on a closed end tube. So this is like taking a string and basically doing a jump rope with it. So if we look here with the first harmonic, the pattern is like you holding both ends of the string. So it's defined by a node on either side. So in the first harmonic, I only have half a wavelength. If I were to continue this pattern on the other end of the first harmonic, I would have a full wavelength. The second harmonic has a full wavelength in it this time. And you can see for every harmonic number that you add down the line, I'm adding half a wavelength. So the first harmonic starts off with half a wavelength, and for every successive harmonic that I move up, I add a half of a wavelength, all the way to the nth harmonic. Alright, so what does this mean in terms of wavelength? So, if you're looking at this, so if this is my tube, and let's say this tube is 2 meters long. So if I have half a wavelength in a 2 meter long tube, then lambda would be 1. So if the length of the tube is equal to half lambda, then lambda is equal to 2 divided by 1 times the length of the tube. So if the length of the tube is 2 meters, 2 times 2 equals 4. Second harmonic, easy. Because I have one full wavelength in there, 2 over 2 just becomes 1. So lambda equals 2 divided by 2 times L, which is also 2 meters. Now down here when we get into the third harmonic. Now let's say this tube is 3 meters long. I only need to go this distance here in order to get one full wavelength. It's all the way up, all the way down, and back to equilibrium. So here, lambda is equal to 2 divided by 3 times the length of the tube, which is 3. My 3's would cancel out, so it would just be 2 meters long. So in the end, your base equation says that wavelength is equal to 2 divided by the harmonic number times the length of the tube. Alright, so let's see if we can use this to solve a word problem. Alright, what is the wavelength of a third harmonic standing wave that's creating a standing wave in a 1.5 meter long tube? So here I'm going to draw my picture, the third harmonic. Remember, for every harmonic it's a half wavelength, so 1, 2, 3, you get the idea, the third harmonic. So if this tube is 1.5 meters long, what is lambda equal to? Lambda is equal to, do we remember our equation from the other side? Yeah? Good job. So we're saying 2 divided by harmonic number times the length of the tube. So we're in what harmonic? Third. So 2/3 times the length of the tube. So 2/3 times 1.5 meters. So lambda equals 1 meter. And we know that if we went all the way up and all the way back down and back to equilibrium, we're just looking at 2/3 of 1.5. So 1 meter checks out. And then we can do all sorts of stuff. If it was at a frequency of 250 hertz, velocity equals wavelength times frequency, so we can use that and start to solve for more and more and more things until we don't want to do physics anymore. But that's it for waves for now.